Okay, off we go. So here's what we were talking about last time. We were talking about symmetry. Again, very powerful, very important, very underappreciated, I believe, method of computing integrals. Extremely powerful. All you need for this to work is to have an integrand that is odd and a domain that is symmetric. And once you've established that, snap your fingers, declare victory. The integral is 0. It's as simple as that. It's totally awesome. Way better when the opportunity permits, when the conditions are satisfied, right? Way better than trying to slice and figure out the bounds and deal with, possibly square roots and other ugliness and antiderivatives. Oh my gosh, the tedium, right? So, awesome theorem. Just do be warned. You got to have both conditions. One of the most common mistakes I see students make when they're trying to use the symmetry theorem is they see a symmetric domain and they get excited about it and they say the integral is 0 and they didn't check the integrand. That argument absolutely makes no sense at all, right? So you do, very importantly, you have to check both conditions. And furthermore, just to be clear, it's got to be over the same line for both of the conditions. If you have odd symmetry over one line and a symmetric domain over a different line, you got nothing. The argument does not work. Okay, so here's a couple different takes on why it works. We talked about these last time. And then we did this example last time where we had what was going to be a brutal nightmare of an integral to compute, right? Absolutely nightmarish. Possibly not even doable. I don't know. I haven't tried. I don't want to try. It doesn't really matter is the point. But the point is this could be completely intractable from a slice and dice, use the fundamental theorem several times point of view. But we make an easy symmetry argument, and I won't go through those details again because we did them last time. Okay. All right. So before I go on to the next thing in the notes, I want to tell you why it is that I like this theorem so much, why I like the symmetry argument, and it's because of how much I used it when I was an undergrad. Now, y'all are largely engineers. I was a physics major, or at least relevant to what we're talking about here was my physics major, and they're not that different. Right? Somewhat different, of course, right? But y'all will be doing lots and lots of integrals in your futures. And I feel, looking back on it, and I don't have any data on this, so this is just kind of subjective based on my memory of the experience, I think about 20% of the integrals that I computed as an undergrad, 0 by symmetry. That's a lot of integrals, right? That's a lot of integrals in your future. Right? That you don't have to slice and find the bounds and do several antiderivatives, some of which might be super ugly, right? Just make a couple of observations, snap your fingers, and declare victory. It's really, really powerful. Right? Big deal. Okay, so, all right, now with that noted, symmetry arguments do need to be full. Complete, right? So here's what I consider to be a complete symmetry argument. This is for the purposes of grading, right, on exams. Certainly on exam 2 coming up real soon, right? Was that Friday? I think it's Friday this week. Is that right? So this is I'm going to say going to be on the exam. Technically, it's not established until the end of today, but I'm pretty sure we're going to make it. So you need to give me these 5 things, right? 5 different things. You've got to tell me what is the line of symmetry that you're talking about. That is fundamental to the argument, right? If you're going to say that something is symmetric, what do you mean? There's lots of different kinds of symmetry, right? You've got to tell me explicitly what kind of symmetry you're talking about. Okay. The reason that line matters, at least concerning oddness of the integrand, is that you've got to establish the oddness with an algebraic calculation. We'll talk about that in a moment. But in order to do so, you're going to need to have an explicit formula for what it means to reflect over your chosen line. right? So we did that in this argument up here. Here was my formula for the reflection over that line. Right? Now, how did I conclude this? Well, we drew a picture. We kind of just saw geometrically, right? You don't have to algebraically derive this or something like that. By hook or by crook, whatever you can do, just as long as you can establish clearly what the formula for the reflection is. I'm going to need to see that. That's part of what we're going to be looking for in the grading. You do have to doff the cap in recognition that the function is odd. Right? Again, conclusions are true because of reasons. Right? We're here for the reasoning. The fact that the function is odd is unavoidably critical to making a symmetry argument. The reasoning that is necessary for a symmetry argument. So you got to give me that. Now this is kind of an easy one. You just got to say so and be correct. Right? You can't declare something's odd when it isn't. That's obviously not acceptable. But you do have to say it. Again, it's part of the reasoning, and reasoning has to get said. Furthermore, you also have to demonstrate it. It is not something that you can just eyeball see in all cases. What it means for a function to be odd is non-trivial. Right? It's part of what we're learning here, and so you got to demonstrate to me that you can actually conclude why the function that you claim is odd actually is odd. And then now again, critical to a symmetry argument is the fact that the domain is symmetric. Again, if you have an odd integrand, so what? That doesn't mean anything until you also establish the domain is symmetric, and at that point, now you've got something, now you've got an argument. But so again, because of how important this fact is, again, just a little quick recognition, doff the cap to the fact that the domain is symmetric being a critical part of the argument. Notice, absent from this list, you don't have to demonstrate that the domain is symmetric. That is usually, I'm going to say, sufficiently clear from geometry in vast majority of cases. That I don't feel like this is a class where we want to get upset about demonstrating why the domain is symmetric. It's usually sort of notationally awkward anyway. It's a distraction. It's not what I'm interested in. I'm perfectly willing to believe that when you're faced with a symmetric domain, that you can just see that, right? And so you don't have to demonstrate, but you do have to state that the domain is symmetric. Okay, so again, 5 things. Make sure to know what these 5 requirements are. If you want to make a symmetry argument, now, I guess technically you don't have to, right? But this is a powerful method, and if you do this, if there is a question that can be resolved by a symmetry argument, and if you do it a different way, then you clearly missed the point, right? So in some sense, you do kind of have to for full credit. But if you want to give me the best solution and therefore get the best number of points, then this is something you need to make sure you know. All right, and then lastly, just a warning. You've got to be really careful using symmetry. It is a risky method to use. Let me explain why. You've got to keep in mind it's about reasoning, not answers. Right? So if you claim an argument of reasoning that doesn't work, for whatever reason, maybe you thought that the domain was symmetric, but it's not. One point of view on that is, well, I made one mistake. But the better point of view is that none of the reasoning you've supplied is relevant to an actual solution. You've made a lot of progress toward a dead end, right? It's not relevant to the question. It's got nothing to do with the question. So if you're going to make a symmetry argument, you're taking a chance that what if I'm wrong, in which case I got nothing, right? So just double check everything. Really think it through. Make sure that you know exactly what needs to be checked, exactly how to check it, and then double check that you actually did that checking correctly, right? Before you decide to just go all in and risk it all, right, on making a symmetry argument. Okay, so just keep that in mind. All right, another example. Now, the purpose of this example is to show you what not to do. This is you can see down to the end, this student gets 40% credit for this question. The question is to compute this integral right here. And the student responds, hypothetical student responds like so. And the student didn't give a complete argument. Now the conclusion is fine, right? The conclusion is true. But this student, let's see here, let's go through the list. Did this student declare a line of symmetry? I don't see where. The students made these vague assertions about the domain being symmetric. Well, it's symmetric through like 4 different lines. Which one are you talking about? This matters, right? This is really important. Let's see here. The student didn't establish what the reflection is. The student didn't demonstrate that the function was odd. Now, the student did correctly claim that the function is odd. The student did correctly observe that the domain is symmetric. But the student didn't back it up with anything meaningful. So, again, right track, wrong implementation. Yes?
Could you switch the order of 3 and 4? Like, could you demonstrate that since F is...
Oh, yeah, I don't care what order you go in. Yeah, totally. As long as it's all there, and, naturally, you can't do a demonstration that F is odd until after you've done the reflection formula. Certain things are unavoidable, right? But as long as it's all there and fits together and makes sense, it's totally fine. Yeah, so I'm not particular about the order, just that they're all there. Okay. All right, so, again, this student gets 2 out of 5. So if this were a 20-point question, the student gets 8. Now, that's frustrating to me as a grader, right? Because I want, right, the student has the right idea. Why didn't the student just give me what I need, right? Give me the argument, give me the excuse. I want to give you points, right? So this student didn't allow me to give them the points that I want to give them. So why would the student do that? Does that make sense? Everybody understanding the point here? So make sure to give me all 5. Okay, another example. This one's just to have another example on the board here. We've got a domain bounded by 3 curves there, one of which has 2 chunks. And y'all are going to have to make sure to remember all of your high school algebra, curve plotting, this kind of thing. These are all standard curves. You should make sure you know pretty much what those curves look like. And you put them together, you identify the relevant region bounded by those curves, and there you go. And I'm going to say eyeball glance. Almost leaps off the page at you. Right? This is symmetric. I missed. Harder than it looked. I keep missing. Come on. There you go. Symmetric over that line. Is that cool? Everybody believe it? Okay. All right, so that being, of course, this line right here. So that's, we've established what the line of symmetry, we wrote it down, right? Clearly indicating to the grader that we've established the line of symmetry. And then now, here's the kind of the tricky part of this problem. In order to establish what the reflection formula is, we've got to figure out what happens when you take a point in the anywhere in the domain or otherwise, and when you reflect it over the line in question, right? So what's the formula for that reflection? Be careful not to play too fast and loose with this. This reflection is not, this point is just not the negative of that point, right? This reflection does not always go through the origin. We're reflecting through the line. It may or may not go through the origin. This is not just the negative of the input point. Does everybody see that? Geometrically, you've got to be careful with that. Easy mistake to make. So how are we going to do this? And again, most of the excuse for me to put this example on here is to show you this little clever trick that, again, I wish I thought of, but I didn't. And that is to notice, let's see here, why don't I get rid of that? That if I make what I like to call a rectangular frame for that point, right? It's hard to see looking only at the red point how that's going to reflect over this sort of 45-degree angled line. But the frame is actually pretty easy. Because this is a 45-degree angle, that green part of the frame is going to reflect to, it's horizontal, so it's going to reflect to vertical. And then the blue part of the frame is vertical, so it's going to reflect to horizontal. And in fact, let me zoom in so we can see this better. So this initial input point, x comma y, right, the reflection of it then is going to be that point right there. And again, you can just look at the picture and you can see that what had been the x coordinate, well, the negative of that is going to apparently be the y coordinate for our reflection, and likewise for the blue. So all together, oh, whoopsie. There we go. So all together then, this reflection is given by that formula right there. So this is just a different example. We've previously seen a relatively easy example for how to find a reflection. Right? We were looking at this one here. We were reflecting over the y-axis. There's the y-axis. Here's what it looks like when you reflect over the y-axis. You're clearly just changing only the x-coordinate, which becomes the negative of what it had. But this kind of reflection here is pretty easy to you just kind of see it from the picture, right? No fancy geometry required for this reflection. But when the line is a 45-degree line, it's not as immediately obvious. This is the little foot in the door, little math hack that will allow you to get what you need there. How's everybody doing on that? Does everybody see the trick? Alrighty. So with that done, let's see here. Let's show. Let's state for the record. Order doesn't matter again, but let's get it on the page. Domain is symmetric, right? Boom. And let's see. I claim the function is odd. There's that. Again. Seems a little silly, but even if you have the algebraic demonstration, you've got to establish that you know what you've demonstrated, right? Again, it's just very fundamental to the argument itself to establish that the function is odd. So just write it down, make sure there's no ambiguity about what it is that you understand in your argument. Okay, so the meat, I suppose you might say, of how are we going to establish that this function is odd? Well, remember, oddness requires demonstrating that when you put the reflection in, you get a negative out, right? That's what it means to be odd. This right here, that minus sign, resulting from when you put the reflection in and you get the negative out. Okay. So, well, let's see if that calculation works out as I've got it done here. Don't forget we've already established what the reflection is. There's my reflection formula. So for the reflection, I plug in negative y comma negative x, because that's what we saw from the geometry. Okay. Now, here's the slightly tricky part, slightly confusing part. A lot of people have a little trouble with this. Let me try to get this on here. And if you want to be really careful about this, you can avoid this problem with a notational change that I don't think is going to be necessary. But if you find this sufficiently troubling, come to my office hours. I'll show you a little workaround that's arguably a little bit more trouble, but might make it this a little bit more clear. I've got to now think about what happens when I plug in this input into that function. Okay, so what you got to remember is that when I call this my function, this is my f, this is my integrand, this is a function of x and y, where x is the first input and y is the second input. So that means this first input that I'm actually going to plug in here, it's negative y. Notice that's the first input that went in. Right? It's because of the fact that I've reflected x comma y. But negative y is now my first input. That means negative y has to go into here where the x's are, because it's now the first input that I'm plugging in. And so you'll notice putting, oh, I missed again, come on. So negative y goes where the x's were. Likewise, let's talk about this minus x. What's the deal with this minus x? What am I doing with this minus x here? Well, that's the second input that I'm plugging into f. That means this minus x needs to go where the y's are, because y in this generic representation of the function is my second input. So it goes there, and thus like so, and like so. Everybody on board with that? Okay. So, gotta be really careful there. This is a stumbling block. This is where a lot of students will make the mistake, and just be very careful how you plug your reflection formula into your integrand function. Okay, and after that, it's just a matter of doing algebra. Let me zoom in so we can see better. The algebra is pretty straightforward. You look at this first term. This ends up being the negative of x plus y. That negative gets raised to the power of 7, which is an odd power, which means I get a negative right here as a result of that, what I have in purple. Now let's see, what about this over here in dark blue? Well, let's see, what is that? That is x minus y. How about that? So, x minus y. There is no sort of minus sign that I need to kind of factor out. It's already x minus y. What do you think? Anybody follow that? So, as required, as it turns out, we do get a minus sign. This minus sign being what I am apparently multiplying by the original value of the function at x comma y, right? So there's f of x comma y. And we've established the oddness. If I can get this to, okay, there we go. Okay, and game over, integral 0 by symmetry. Okay. Everybody see how this stuff works? Okay. Just for fun, let's consider our options, right? What would have happened if I hadn't made a symmetry argument? Well, you can make the case that this is, in fact, just a polynomial. It is pretty doable, I suppose, right? But also, don't forget, you've got to do it over this domain, and this domain, I'm going to say, is not a very nice domain, because no matter how you slice, you're going to hit corners. It's a question of which corners, depending on which way you slice, right? But you're going to hit 2 corners, which means you are going to have 3 integrals. And by the way, notice that one of your inside bounds is going to be a reciprocal, which means your outside integral is not going to be a polynomial. It's going to have reciprocals in it. Again, it's doable, but it's just a little bit more trouble than you're probably going to prefer. Everybody on board? All right. Let's see another example. Yeah, so now I gave away the game and how I wrote the notes here, right? But before we get to the surprising punchline on this example, let's think about how we might approach this on an exam, right? Let's put ourselves in an exam mindset, and I'm going to say in an exam mindset, you'd look at the triangle, and you'd say, okay, well, let's plot these points, 0, 2, and let's see, -1, 0, and 1, 0. Oh my gosh, symmetric domain. Oh my God, look at that, odd integrand. Right, you get all pumped up because odd and symmetric. Oh my God, this integral 0 by symmetry, easy, boom, right? And the argument doesn't work. So this is a great example of the landmine aspect of this that I was talking about before. That it's really easy to be tempted to go down the road of trying to make a symmetry argument when in fact that is a dead end. There is no symmetry argument here. It's not that we didn't make the proper symmetry argument. It's that there is no such argument. The problem being, of course, that the domain is symmetric over the y-axis and only the y-axis, right? Whereas the oddness, if you think about it, in order to get the oddness, I would need my reflection formula to turn y into negative y, which means as far as oddness goes, I'm reflecting over the x-axis, not the y-axis. It's not a question of what do you reflect parallel to. It's a question of what are you reflecting over, namely perpendicular to. Right? So this is a nasty little landmine, right? I don't want you all to step on it, right? So be on the lookout for this kind of thing. There is no symmetry argument to be made. Any efforts made toward a symmetry argument here are just wasted pencil lead, or pen ink, sorry. Right, black pen required. Right? Everybody happy with this example? Okay. All right. Okay, so yeah, just super careful, heads up. Make sure it works. Double check the details. All right, so now everything we just did is in 2 dimensions. Let's talk about 3 dimensions. We live in a 3-dimensional world after all. Y'all are going to be doing engineering in a 3-dimensional world most of the time, right? So is there a 3-dimensional version of this? Yeah, absolutely. It's almost exactly the same. The only thing that we have to change is to make sense out of what we mean by a reflection in 3 dimensions. And in particular, we're going to talk about reflections over a plane, which, again, every time you look in the mirror, you are experiencing a reflection through a plane. The mirror is the plane. Right? So arguably, this is the most natural and relatable notion of a reflection, is in 3 dimensions and through a plane. So again, the picture is exactly what you think, and the subsequent definitions are exactly what you think. Reflection going in has to result in a minus sign coming out. That's what oddness means, right? Just like in 2 dimensions. And a domain being symmetric, I'm going to say again, it's exactly what you think. This is how you'd write it down in notation. We don't need to get bogged down in that. It's exactly what you think. And the theorem is almost character for character, exactly the same, right? So we need our integrand to be odd. We need our domain to be symmetric. We need both of these conditions to apply. Again, it's got to be both of them. If it's just the one, you got nothing. All right, be careful about that. And it's got to be through the same plane for both of these symmetries. Otherwise, again, just like the last example we saw, you got nothing. Okay. Now, obviously, in my physics days, it was the 3-dimensional theorem that I used much more often than the 2-dimensional one. So this, in practice, is arguably the one that you're going to be using the most. So here's an example. Again, it's very straightforward once you realize what direction we're going on this. But let's take a moment to recognize how this being the unit ball would make this a bummer of an integral, right? Now, we do have our recently acquired trick of spherical coordinates, right? And that does make this quite a bit more doable. But think about when you convert this integrand into spherical coordinates. And don't forget dv is rho squared sine phi d rho d phi d theta, right? I mean, this is going to have a lot of trig in it. And so you're going to be doing a lot of trig integrals. And again, it's not that it can't be done, but that's going to be pretty inconvenient. Okay. All right. So our domain is the unit ball. I've got a million symmetries. It's symmetric through every plane that goes through the origin. Lots of options. That's it's a good sign, right? By the way, my own personal instinct, right, and what I want to encourage you all to try to develop in yourselves as well, is that eyeball glance your domain every single time you do an integral. just ask yourself, are there any obvious symmetries that I should be, that should raise an eyebrow, perhaps, right? Just look and see. And if it does, that doesn't mean you can make an argument, a symmetry argument, but it means it's a possibility, and as powerful and quick and useful as this method is, it's worth kind of thinking about it. So in this case, I'm going to make an argument through the xy plane. You'll see why in a second. Through that plane, here's how you reflect. Now again, this is a hand-wavy geometric argument, but your xy plane is horizontal. If you reflect through the xy plane, all that happens is what had been your original z, the negative of that becomes your new z, right? Reflecting through the xy plane just introduces this minus sign on the point. Again, geometric appeal. And I mean, we've already made the observation the domain is symmetric. Again, you don't have to justify it. You just have to say so. Again, doff the cap in recognition that that is a critical part of the argument. We establish, we state for the record, again, doff the cap, that the function is odd, and the meat of it, how do we show that the function is odd? Well, I take this reflection, I plug that into this function, and again, keep track of what goes where. Now, conveniently here, the first coordinate is x, which is what the first coordinate's supposed to be. So plugging in x where x should be is, yeah, that's easy. Y where y is, yeah, of course. And all that's happening here is you're plugging in minus z where z is. And so this minus sign here gives rise to that minus sign there, which when you cube it gives you that minus sign there, namely that, which is exactly what you're supposed to get. So no big deal doing that algebra, right? Just got to do it delicately and think it through. And we've done all 5 of our required, let's see here, let's just document for the record. We've named the plane, we've formula for the reflection, we've declared symmetry of the domain, we've declared oddness of the function, and we have demonstrated oddness. And so integral 0 by symmetry, no trig, no spherical coordinates, no slicing and dicing, no difficult geometry. Boom. Everybody good? Okay, so again, be on the lookout, right? One other thing I should mention, these opportunities don't announce themselves in the real world, right? So in your, when I say the real world, I mean your engineering classes, right? In your engineering classes, rarely will it be the case that they'll say, here, compute this integral, by the way, use symmetry, right? No, they're going to just say, here, compute this integral. So you've got to be the one to make the realization that symmetry is a good idea and applicable, and then after that, yeah, you've got to actually do it. Okay. So be on the lookout. But side note, there are several old exam questions that you're going to, several is an understatement. There's a lot of old exam questions that I've given over the years in my multivariable calculus classes, 219, 212, where here, compute this integral. And it's going to be a rough one unless you use a symmetry argument, and then it's easy. And you'll notice in the phrasing of those questions, most cases where I use a symmetry argument to solve an integral on an exam, I don't announce it as such on the statement of the question. So, heads up. Okay. All right. So, moving on. So 5.6, by the way, my hope is to finish this today. I know we've got 15 minutes left, but this is a bunch of applications. I want you to see the applications, but again, my focus here is on multivariable calculus, not physics, right? And so a lot of the sort of the build-up to our punchline results is, again, not really the focus of this class, and in a situation where, again, time is valuable, we're behind schedule even, right? Tough choices about what we spend class time on, and a lot of what's in 5.6 just doesn't make the cut. I start here with an example of what it means to take a weighted average of some numbers. You could make the case that this average, now notice, there are 6 numbers, which I've added and divided by 6, so that's just plain old, good old, nothing to it, regular old average of those 6 numbers. Or, I mean, if you want, you could think of this as an average of 3 numbers. The numbers are 4, 7, and 8. But for whatever reason, I want to double count 4 and I want to triple count 8. But, you know, why you'd want to do that, so we're going to see some examples to follow. So the point is that can be thought of as a weighted average of 4, 7, and 8, and here's how the arithmetic kind of can be reconceived to double. You know, what does it mean to double count? Well, the double count means that I've got to multiply it by 2, and that contributes then 2 to the denominator, because that's what happened there. Right? Or you might say what happened there. Take your pick. Likewise with the others. So generalizing this is the formula for the weighted average of a list of numbers, and it's just a rip-off of what we saw in this example right here, right? And in particular, notice the role that the weights play, right? The weights, you know, what am I double counting? What am I triple counting? What am I 4.3 times counting, right? There's no need for the weights to be integers at this point. The weights just go here and here. And that's what it means to do a weighted average of those numbers. Okay. So it's a nice idea. Ultimately, again, don't lose track of this point, a weighted average is literally an average. It's just that you're counting some of them more times than others. Okay, now just because it's so relevant to us in this course, I think this is a nice example. Hypothetical scenario. We've got some course where there are 4 graded items in the course, right? Exams 1, 2, 3, and 4. I just wanted to keep the example streamlined, right? But the what I'm trying to kind of not so far off kind of model is this class, where our course grades in this class are going to be computed by a weighted average, right? Different graded items, different weights, of course. But just to keep the numbers simple, our friend Bob got these grades on the exam. These are what we're doing an average of. So those are the grades, and they go like so. Right? That's where we put the things we're taking an average of. The weights were given to us 20, 20, 20, 40. So 20, 20, 20, 40. Just following the general formula up there, that's where the weights go. And you've got yourself some arithmetic. You can punch that up, and Bob's course average is 2.964. Let's see, what is that? That's good. Well, that's just under the stereotypical B, 3.0, which means he's comfortably within the B bin, right? The B range. So his course grade is B. Does everybody follow how that calculation went? It's just straight up a weighted average. Again, very relevant to our course. This is how ultimately my spreadsheet will compute the course weighted averages for students in this course. And so if you want to be able to anticipate, right, how your grade's looking and what's your status and what do I need to get on later exams in order to account for earlier exams to get the whatever weighted average that you're hoping to be able to get because of whatever reason, this is the kind of arithmetic you're looking at. All right. Okay, so the reason I show you that is because ripping off from that formula allows us to talk about the average value of a function. And so again, we're looking at the values of the function. That's what we're trying to average. And we use size in the domain as weight, which is kind of that right there, kind of, sort of, if you will, right, loosely speaking. And there you go. This definition that we're making here for the average value of a function is just a ripoff of the simple arithmetic idea of a weighted average. And then you notice very quickly that that is just b minus a, and so a nice sort of streamlining of our formula is that right there. And in practice, this is what most people work with. Okay, so easy examples. Y'all can read the single variable example there. I point out that you can do the same thing in multivariable. Again, there you go. We are averaging the values of the function where we're using size in the domain, namely area, now that our domain is two-dimensional. Area are the weights. Again, shameless ripoff, previous formula. And again, that being just area. Again, that's an easy little streamlining of the formula. So let's look at this example. Let's think about how we want to look at this function f of x comma y equals x squared, defined on the unit disk. Right? This is a function of x and y. Very convenient how it depends on y and then it doesn't. Right? So it's still a function of x and y. And on that unit disk, how would I compute the average value? Well, again, average value, plug it into that formula. There you go. Oh, whoops, there you go. The area here, easy. Barnyard variety geometric formula from high school. That's the area of the unit disk is pi. Right? Is everybody happy? Everybody with me? And then all I've got left is just I've got to compute a double integral. So this is a nice application of double integrals. Double integrals are doing most of the heavy lifting for computing the average value of a function on some domain. And so how do we compute this integral? Well, take your pick, but this being the unit disk, you look at the picture, consider all the tools in your toolbox. You could do this in rectangular coordinates, but it's really a lot easier if you do this in polar coordinates because of how easy the bounds are going to be, right? So what would have been square roots in my bounds, had I done it in rectangular coordinates, become constants in my bounds because of how very nicely the unit disk works with polar coordinates. dA, of course, RD theta. Don't forget your stretching factor, right? Write it all down all at once, RD theta. And yada yada. Cool? Yeah.
Is there a simple way to do mean absolute value, like if you wanted to, for instance?
Yeah, but then the thing you want to average is literally the absolute value, and so you just put absolute values around this. And that leads you to the unfortunate scenario where you'd have to then break the domain into two separate chunks, one where is it positive, one where is it negative. So, tedious implementation, but morally the same idea. Yeah.
Thank you.
Yep. Okay. Here's a pretty nice and increasingly physicsy idea of why we'd want to compute weighted averages. It's because that's what the center of mass is. And center of mass, anyone who's had a high school mechanics physics course will probably recall center of mass is a really important thing for a lot of purposes in physics, right? A pretty elegant definition of the center of mass. It's the weighted average of the position. Nice and succinct. Nice and streamlined. Now, why would we care about such a thing? There's a little example here, and I encourage you to look at this example. When you have a couple of masses, like so, this idea of weighted average of position, I mean literally, weighted average where I use the masses as the weights. So all that is straight up plug in the weighted average of position. Gives you the balance point. That's where the torque is 0. So like you take my pen here, for example, and if I try to balance that on my finger, see if I can do that. Right? Why does it balance on my finger? Well, it's because, I mean, there's two different torques. This side of the pen over here is applying a torque, what from your perspective would look clockwise, right? But this side of the pen is applying a torque that from your perspective would be counterclockwise. And the two torques are exactly the same, but in opposite directions, so the actual total torque is 0. And that's why it's not rotating, aka that's why it's balanced. Right? So nice little exercise. You can, and I encourage you to do this, that when you balance and this is of course just an oversimplified example, but two little pieces of mass, and if you compute the amount of torque that the first mass sends counterclockwise, and you compute the amount of torque that the second mass creates clockwise, understood to be torques around a balance point that's at that point, computed by this weighted average formula, you can directly confirm that that total torque is 0. That's a nice little exercise. It's just algebra, not that much to it. Okay. All right. So there is a tricky little bit that we need to talk about before we probably call it a day. And that is, what do I mean by an average of position like so? What do I mean specifically by this integral? There's something very weird about this integral, you may have noticed. This is our first time to see an integral where the integrand is a vector. What's that? Right? We've never done such a thing before, right? So you should be a little weirded out by the fact that our domain is a vector. What does that even mean? The good news, it actually is pretty straightforward what that means. What am I going to do to this vector? Well, the first thing, I multiply it by a scalar. How do we multiply vectors by scalar? One coordinate at a time. Each coordinate independent of the other. No problem. And then I'm going to be adding all that stuff up. How do I add vectors? One coordinate at a time, totally independently of each other. So the beautiful thing about that, right, this integral, this vector integrand double integral, yeah, you just compute the coordinates one at a time. Here's how you compute the first coordinate of this weirdo thing that we're encountering for the first time. And here's how you compute the second coordinate, third coordinate, et cetera, et cetera, et cetera. And then finally, that's how you compute the last coordinate. So you just do one coordinate at a time. Okay. All right, and let's see here. I'll bet you we're pretty close to out of time at this point. Why don't we draw the line right here? We'll pick up there on Wednesday. But we've already not finished section 5.6, so sadly I didn't make it. We're not going to have 5.6 on the midterm, right? But 5.5 is where we're going to draw the line. Okay. See y'all later. Have a good one.